It's just, that makes a lot of sense. I'm excited to read your book. Anyway, we need to move on, and hopefully there'll be some time at the end of the presentation for questions too. And our next speaker, James Carter, has been, I think, involved with the NPA from the beginning, or at least maybe one of the first early years. So I believe, have you attended more than a dozen of these over the years?
Yeah, I've only missed a couple.
Only missed a couple. So here's a real veteran. For those of you that aren't familiar with his work, he wrote a book some 15 years ago and did some really interesting models. I was hoping he might bring them for Saturday. They're not going to be there. And today's presentation has nothing to do with those models, but they're fascinating. Like a lot of NPAers, he's interested in a lot of different things. Today he's going to be talking about the evolution of matter through cosmological time. Very interesting talk. And so here we have James Carter. By the way, the papers are available if you want to follow along as he talks about it.
Okay, well, what we're going to be talking about today is basically the creation of the universe. This is kind of an alternative theory to the Big Bang theory. And basically, I'm not changing the standard model of physics. We're using, this is basically a history of the hydrogen atom. And we're only making one change, and that deals with the mass of the electron. Now, these are some of my models of the electron and the hydrogen atom. I use what I call the circlon, and it's 3 sets of coils. There's the smallest primary coil, which forms the basic structure, and then it's wound into secondary coils, and then the tertiary coil is the main coil. Now, you can picture the hydrogen atom any way you want. I'm just using these models to kind of illustrate what I'm going through here, but you don't have to use these models for this theory that I'm presenting to work. Okay, now if we can go to the next picture. This is the beginning of the universe, and basically we aren't starting with a singularity. We're starting with 2 particles, an antiproton and a positron. These are basically like the antiprotons and the positrons of today, except between the 2 of them, they contain the whole mass of the universe. They're very massive particles, but they work the same way as the particles do today. Now, you have to start someplace. The Big Bang theory starts with a singularity. I'm starting with 2 particles, which are known particles, which basically the universe is still today made up of protons and electrons that are put together in a lot of different ways. So eventually these 2 particles were separate in space, and they came together. And you can go to the next slide here.
Takes a minute to load them, I'm sorry.
You didn't find it.
I got it, it's loading.
Oh, okay.
It's very slow, I'm sorry.
Okay, this is basically how these 2 particles came together, the positron and the electron, to form a basic hydrogen atom. And you can go to the next one now.
You can talk while it's waiting.
The 2 particles came together and they formed this hydrogen atom that just sat in the universe for a long time. But what was changing is the mass of the negative particle, the antiproton, was actually losing mass and getting less and less massive. So the masses of the 2 particles were growing closer together. And eventually they got to the point where the positron was captured by the antiproton and it formed an anti-neutron. This neutron, you can go to the next one. This neutron sat in the universe for a long time, and slowly its internal positron, or its anti-neutron, was getting to be smaller and smaller mass until they reached the point where their masses were identical, and they became a particle-antiparticle pair. And what happened, you have this neutron, which is basically an antiparticle-particle pair that split into two neutrons. It didn't annihilate into photons because they were locked together in a neutron. And when they became equal, they annihilated and split into two neutrons. And then these two neutrons, you can go to the next one, split into 4 neutrons. And then 8, and then 16, and 32, and 64. And as long as they remained the same mass, they were able to keep splitting and splitting. And this process happened, we can say 256 times. At 202 to the 256 power is very close to what the number of protons are in the universe. Eddington estimated that it's 10 to the 80th power. And so I'm showing each single split, and this picture represents all the particles in the universe. Now what we have here is 2 to the 256 power neutrons, and they're all floating in the universe. Well, what happened at the end of this cycle, the antiproton kept losing mass to the point where they were no longer particle-antiparticle pairs, and the anti-neutron became, in effect, less massive than the positron and became an electron. And the positron basically became a proton. So now, the neutrons that we have here are not anti-neutrons, they're actually neutrons. Okay, you can go to the next one. And so now the universe is filled with this.
I can't get the next one. I don't know.
Cloud.
It's a different kind of file. I can't get it. I'm sorry.
Oh, you can't.
Sorry. I can get all the rest of them. I'll get the. Sorry about that.
Well, that's okay. So these neutrons spread out.
Well, this is the next one.
Okay, this shows these clouds in the universe. There are these neutron clouds that are just kind of segmenting and separating, kind of like atmospheric clouds do. And eventually they reached a point where the electron kept getting less and less massive until the neutrons all became unstable and all started to decay at the same time. So now you've got the universe is filled with this mass of decaying neutrons that are actually decaying into protons and electrons. And the protons and electrons start combining together into hydrogen atoms, and they are emitting photons. And it is this massive blast of photons, which is, you can probably go to the next one, which forms the 2.7 degree cosmic background radiation. Now at this point, the hydrogen atom its spectrum produced photons with much longer wavelengths than they do now because of the mass. The electron was so much more massive than it is today, it would produce a spectrum with longer wavelength photons. Yeah, you can go to the next one. This one.
Oh, I just got it. Okay. You don't want to look at this?
Well, this kind of shows